This video covers section 1 of chapter 8 on sampling distributions of proportions. We'll start by looking at what a typical inference problem will look like. We'll define the sampling distribution. We'll use 3 approaches to get at sampling distributions, and we'll apply the empirical rule. In the 4 stages of statistics, we are still in probability, and we're talking about proportional sampling distributions. So here's the type of problem we'll be interested in after we get to inference. If a sample of 100 students has 0.13 left-handed, so 13% of the sample is left-handed, would you be willing to believe that the proportion in the population is actually 10%? So our sample is much higher than that. But is it an unbelievable amount higher than that? The way that we'll solve this is to make a temporary assumption that the population proportion is what we're asking you to believe it is. And then we use the methods that we have learned and that we will be learning in this section to find the probability that the sample proportion turned out as weird as it did. If that probability is too low, then we'll reject that belief that the population proportion is actually 0.1. So let's talk about finding these probabilities. So if we know what the population proportion P is and what the sample size N is, what we want to be able to do is find the probability that the sample proportion P hat falls in a certain range. In order to do that, we need to know how P hat is distributed. Now, P hat can denote a single statistic, that's the proportion in our sample, or we can use it to denote a random variable. That is, it's the proportion in a sample that is chosen randomly. From context, the meaning will be clear. Now, a sampling distribution of a sample statistic is the probability distribution of the values that are taken by the statistic if we repeatedly choose random samples of the same fixed size. Remember that probability distributions are summarized using center, spread, and shape. Just to review quickly, if we take a random sample of size n from a population that has a proportion P in the category of interest, the sample proportion is computed by taking the count in the sample, that's X, and dividing by the size of the sample, that's N. Now that P hat is a statistic, it is the proportion inside our sample, but we can also treat it as a random variable. Its value depends on the random selection of the sample. So we know the way it is distributed can be summarized by the mean, which is P. Overall, we expect the proportions in our randomly selected sample to average out to the proportion in the population. We talked about how to compute the standard deviation. And we know that if n is big enough, the shape of the distribution is approximately normal. And remember that we can use the empirical rule or our computers or spreadsheets to find these probabilities. Remember, we had to make a few assumptions in order to be able to make the calculations that we were going to do a little bit simpler. The first of these is that the population has to be at least 10 times the sample size. That's so that the selections that we make will be approximately independent, which is required to make sure that standard deviation computation is approximately correct. We also need n times p and n times 1 minus p. Remember, that's the number of expected successes and expected failures inside the sample. Both of those numbers need to be at least 10. That's so that they're big enough to guarantee that the distribution is approximately normal. So we've got three approaches to understanding the distribution of sample proportion. We have an intuitive approach. We can get our hands on and play around with some numbers, and we can look at it theoretically. What we'll do is start with intuition and see that experimental results seem to confirm our intuition, and then we'll tie it all together with a theoretical approach. So let's start with intuition. So let's say that 1 in every 6 M&Ms is blue. That means if I choose one M&M at random, so here we're talking about n equals 1, the probability that the M&M I picked is blue is 1/6. That means the probability that I pick an M&M that's not blue is 5/6. That gives rise to the histogram shown at the bottom of the screen. Notice that it's very strongly right-skewed. And recall that the shape of this distribution is going to be important because as we increase the sample size, the skewness of the histogram, or the skewness of the distribution, will go down. It will approach becoming normal. So again, thinking of blue M&Ms, are we talking about a categorical or a quantitative variable? What about the sample proportion? Is it categorical or quantitative? What do we need to report about the distribution for the sample proportion to give a summary? Well, the underlying variable is categorical, blue or not blue. P hat is a random variable, and it's quantitative because it's a number. Since it is a random variable that's quantitative, then to talk about the distribution, we need to talk about the center, the spread, and the shape. Here we see an experiment where we're going to roll a single die and count how many times we see a 6. Now we're assuming that this die is fair, so the probability of getting a 6 is 1/6. So if I roll the die once, I see I got a 4, so that's going to count as a 0 in my histogram. I'll roll again, I got a 1. I'll roll again, I got a 2, 5, 5, 6, 1, 5, 2, 3, 1, 3, 3, 4, and 6. So every now and then I'm getting a 6, and every time I do, that's changing the distribution over here. What do you think the probability is that we get a 6 on each roll? Well, we've already mentioned it's 1/6. So if I roll this die a whole bunch of times, what proportion would you say should give us a 6? Well, in the long run, the probability histogram for rolling a single die ought to be have a height of 1/6. That's the actual probability of getting a 6. Above 1, remember this is counting the number of times we get a 6. And 5/6 of the time it should be above 0. So let's reset this. And I'm going to roll 100 times, and we're going to do it real fast. So let's see if we can, if our intuition here comes to fruition. Out of those 100 rolls, it looks like we got a 6 11 times, and we got not a 6 89 times. That's a little bit less than we would have expected. Notice the expected values are given here with the blue histogram. Well, if I do this another 100 times, maybe it'll get closer. Now I've got a 6 1/8 of the time, so that is maybe a little bit closer, but it's still low. if I keep doing this, in the long run, our expected value, the expected proportion of sixes that we get should be pretty close to 1/6. So now we're up to 0.16. Remember, 1/6 is 0.16 repeating, so we're getting closer. Now, what does this distribution look like? Well, it's very strongly right-tailed. Our peak is over 0, and we've got a tail over 1. So, what happens as we increase the number of dice that we roll? Let's say we roll 6 dice. How many 6s would you expect to see on each roll? Well, since the probability of getting a 6 is 1/6, I would expect there to be 1 6 in each roll. Now, it could be more, it could be less. So on our first try at it, we got 2 6s. At our second try at it, we got another 2 6s. Let's do another 10 real quick. And we see that we got 0 42% of the time. This is out of 12. So over here we see that that happened 1, 2, 3, 4, 5 times, 5 out of 12. We actually got the one that we expect 1, 2, 3, 4 times. We got 2 twice. Those were the very first 2 rolls we did. We never saw 3 6s, but we did see 4 6s once. Let's do another 10. And another 10. And another 10. Is this what we expected to see? A right-tailed distribution? Well, remember, our expectation was that there would be a peak over 1. And right now it looks like the peak is over 0. So let's do a whole bunch more of these. And there, sure enough, you see in the long run that peak appearing over 1 and not 0. 1 is the most likely outcome. Theoretically, the distribution should look like this. And our experiment came pretty close. Is this normal? Well, no, it's still right-tailed. Remember, to be approximately normal, the number of expected successes and expected failures needs to be at least 10. So since our probability of success is 1/6, that means I'm going to need to roll 60 dice. No, I can't roll any more than 30. And our distribution on this little tool is getting smushed over there. So this isn't going to give you a good picture. But we know what happens as the number of dice we roll goes up. So I just showed you 6 dice. Let's do 12. Let's double it up because that'll give us another good picture. And see if this looks more normal in the long run. With 12 dice, remember, we should expect 2 as our most likely outcome. There's the bar over 2. And sure enough, it's leading the race right now. Here is the model distribution. Here's what we would expect to see. And it looks like 1 is a little overrepresented and 3 is a little bit underrepresented. If I run this again, in the long run, I would expect each of these bars to get closer and closer to where they ought to be. And we kind of see that happening. Those gaps are shrinking a bit. Is this more normal than the last one? Yeah, I would say so. It's still right-tailed. But there's more room for a tail on the left. That's the critical thing here. That's why we want the number of expected successes and expected failures to be at least 10. Because that would be the sort of the how much room there is for a tail on the left and on the right. As we go up and we increase the amount of room for a tail on the left side, this looks more normal. And again, I know that picture's getting squished. So that's what's going on here. So now that we've seen some experiments, let's talk about some theory. The central limit theorem is one of the most important theorems in the mathematics of statistics. It tells us that a sample statistic will approach a normal distribution if the sample size is large enough. We've seen that sort of intuitively. We saw it with our experiments. Proving this theoretically is something that's far beyond this course. It requires some good stuff from calculus and some other higher level mathematics, so we're not going to get into that. But let's talk about the implications of the center. We know that if the population has proportion p, the center of our distribution has mean p. We say then that p hat is an unbiased estimator of p, because it ought to be close. It shouldn't be biased one way or the other. In order for that to be true, our sample has to be random. If the sample is not random, we might be introducing some sort of bias, either knowingly or unknowingly. That notion of randomness is critically important. So we've talked about the center. Let's talk about the spread. Remember that for this distribution, the standard deviation is given by this formula, which we saw back in the section on binomial random variables. Now, the important thing here is the n. Notice that n in the denominator of that fraction underneath the square root. As n gets bigger, that is, as the sample size gets bigger, that fraction gets smaller. That means that as n goes up, the spread goes down. In order for us to use this approximation to the standard deviation, we have to have that the population size is at least 10 times n. Remember, that's our criterion for our selection of the sample to be approximately independent. So the population is important for the standard deviation computation. Now we know the shape, as long as n is big enough, is approximately normal. Because it's approximately normal, we can find probabilities under the normal distribution that correspond to things that we care about. So here's an example. Remember that the proportion of blue M&Ms overall is 1/6. We'll round it to 0.17. If I repeatedly take samples of n equals 25, what would we expect about the distribution of the proportions in our samples? Well, the measure of the center ought to be the same as the center in the population. Now, that's 0.17. What about the spread? That's the standard deviation. We compute using our formula, and we get about 0.075. The shape, well, we're not up to normal yet because the number of expected blues in each sample is 4.25. That's n times p. And that's quite a bit less than 10. So let's bump up the sample size. What about if n equals 75? Well, I would expect p hat to have a distribution that was centered, again, at the population proportion, 0.17. Now, because n got bigger, I expect the standard deviation to get smaller, and sure enough, it does. It's now 0.043. Now, what about the shape? We do satisfy the criterion now for approximate normality because n times p is now 12.75. That's bigger than 10. And n times 1 minus p is far, far bigger than 10. So we're good there. We can use the normal distribution to approximate some probabilities. Now remember that if a random variable is distributed normally, an actual sampled value, so an actual value of the statistic we're interested in, the probability is 68% that our observation will be within 1 standard deviation of the mean, 95% that it's within 2, 99.7% that it's within 3. So for sample proportions, there's a 68% chance that our observed proportion in our sample is within 1 standard deviation of the population proportion. Similarly, there's a 95% and 99.7% chance that the observed sample proportion is within 2 and 3 standard deviations of the population proportion. So here's an example. Remember that for our blue M&Ms with a sample size of 75, p hat, the proportion in our sample, would be distributed approximately normally with mean of 0.17 and standard deviation 0.043. So the empirical rule tells us that there is a 68% chance that p hat is within 1 standard deviation of the mean, that is between 0.13 and 0.21. Similarly, if we go up and down by another standard deviation, there's a 95% chance that our observed proportion will be in that range, and a 99.7% chance that our observed proportion will be within 3 standard deviations of the mean. Remember that the sample has to be big enough to use this. We wouldn't use this if our sample size was only 25, because remember, the number of expected blues in those samples is less than 10. Remember that later on when we're doing inference, we're interested in some particular values for the area between two symmetric z-values, so like between plus and minus whatever. The values that we're going to be interested in particular are 90, 95, 98, and 99. Just to refresh your memory, and again, you don't have to have these memorized because you can get these from your calculator very quickly and easily, that for z, the probability is 0.9 that z is in this interval, so the z value we're interested in is 1.645, and so forth for those other 4 values that we care about. I'll come back to these in just a moment. So here again, we're looking at our blue M&Ms, where the proportion in the population is 1/6, or 0.17. For a sample size 75, we know that p hat should have mean 0.17, and the standard deviation should be about 0.043. So what does this rule tell us? Well, to get 90% of our 90% of the time, a sample that we choose will have a proportion within 1.645 standard deviations of the mean. That means that the proportion in our sample will be between 10% and 24%. So again, 90% of the time, that's this 90% over here, we would expect to see a sample that has a proportion between 10% and 24%. Similarly, 95% of the time, we should see a sample proportion between 9% and 25%. 98% of the time, our sample proportion should be between 7 and 27%. And 99% of the time, our sample proportion should be between 6% and 28%. So remember, one type of inference problem we're going to be interested in is one that looks like this. If we sample 100 students where in the sample 13% are left-handed, is it feasible to believe that the proportion in the population is 10%? The way that we are solving that, or we're going to solve that, is to make the assumption that the proportion in the population is 10%. Then we're going to compute the probability that our sample proportion looks this crazy, this weird, 13%. That's way too high, right? So let's find that probability. So let's look at that question. If the sample of 100 students has 13% left-handed, can you believe the population proportion is 10%? Our approach here is to ask these questions in this order. What are the mean, standard deviation, and shape of the distribution of sample proportions? Once we know that, we'll ask, is 0.13 an unusually high value? Is it way out in the tail of p hat? If it is way out in the tail, then we would not believe that p is equal to 0.1. If it's not too far out in the tail, we can believe that p is equal to 0.1. So let's answer these questions. I'm assuming the population proportion is 0.1, so that means p hat ought to be centered at 0.1. So the mean of p hat is 0.1. I do our computation for the standard deviation. Remember, that's the square root of p times 1 minus p over n. That comes out to be about 0.03. Actually, comes out to be exactly 0.03. What's the shape? Well, to know the shape, we want to know if it's approximately normal. To be approximately normal, n times p and n times 1 minus p have to both be at least 10. And we just barely squeak that in. N times p is equal to 10. So we're good. We can use the normal approximation. So now, how big of a number is 0.13? Well, notice that 0.13 is one standard deviation above the mean. So to see a sample that has a proportion that's as high as 0.13 or higher, that probability would be the area out in that right-handed tail. So just to kind of give you a better sense of what's going on here, picture our normal distribution. I'm going to kind of sketch it in right here. Our center is at 0.1. And if we go up by one standard deviation, there's our 0.13. If we go down by one standard deviation, that's 0.07. Remember, there's 68% of the area in between those two. That means in this tail, which represents all of the samples that are as strange or stranger than ours. Remember, ours saw a sample proportion of 0.13. That's unusually high. That area has to be 16%. There's also 16% in the other tail, but I don't care about that tail. That's 16% as well. Okay, so the empirical rule tells us that the probability is 16%, 0.16, that p hat would take a value of 0.13, that's one standard deviation above the mean, or more. So can we believe that p might be equal to 0.1 and that our sample was unusually high just due to randomness? Well, sure. A probability of 16% is not terribly low. Later on, we're going to establish our standard cutoff at 5%. But since this is 16%, that's well above, we're good there. So to sum up, this lecture covered sample proportions, the way that sample proportions are distributed. So we talked about this type of problem we're going to be solving with this, and that's a typical inference problem. The last example on the last slide was a good example of this. So we think the population might look like one way, but our sample looked a different way. It was unusually high or unusually low. We evaluate that by figuring out how weird our sample is by finding the probability of getting a sample as weird as ours or weirder. We looked at the way that the sample proportion was distributed, and we defined that sample proportion distribution. We looked at three different approaches to understanding these sampling distributions. We kind of thought about them intuitively. We ran through one experiment to get a better sense, and then we wrapped it up by looking at the theoretical underpinnings of the sampling distribution. Once we know some key facts about our sampling distribution, we were able to approximate it by using our measures of center, spread, and shape. The central limit theorem tells us that as long as the sample is big enough, this thing looks approximately normal. And we use the empirical rule to actually find some probabilities. Now, with our calculators, we can be more precise than just having to use the empirical rule, and I hope that you will do that as you go forward.